we've talked about the processes that occur in a star up to about 8 solar masses, 8 times the size of the sun. And that star ends up with its core shrinking. Degeneracy becomes very important when L gets really small, and the core ends up being supported by what's known as electron degeneracy pressure. Now let's talk about stars above 8 solar masses. So the neutron star. Now for a neutron star, the mass of the neutron star is greater than approximately 8 solar masses. I think my solar mass symbol was a bit rubbish then. Okay, that was I didn't want to undo that. It's a circle with a dot. So the mass of the star that we're considering now is greater than approximately 8 solar masses and less than approximately 30 to 40 solar masses. Now these numbers are subject to revision, of course, as we learn more and more. Okay. Neutron stars are produced in a similar way to white dwarfs. Okay, so we have a star that force inwards is due to gravity, force outwards is due to either gas and or radiation pressure. In larger stars, you could argue, which I think is fair, that there is gas pressure. That basically means the pressure, force per unit area, the pressure associated with particles, like physical particles with mass, matter, bouncing around and creating collisions, and in the collision there's a change of kinetic energy. There's a change of velocity, which is an acceleration, which means there's a force. All the standard stuff, the standard argument we use for what causes pressure. But there's also radiation pressure, an outward pressure associated with electromagnetic radiation. Now that's an interaction, so we have to use the particle model to describe it. As the star gets bigger and bigger and bigger, gas pressure gets less and less important, and radiation pressure gets more and more important. In the sun, gas pressure is massively dominant. In the bigger stars, radiation pressure becomes far more important. And that supports the star. The star is stable until it starts to die. And this is core runs out of hydrogen. And when that happens, core collapses. Outside the core expands, as we've discussed before in significant detail, and that happens until a new fusion reaction starts, and that process keeps going. And by the process, what I mean is the core now stabilizes. It's smaller than it was, so it's hotter. Stabilizes, burns the fuel, whatever the fuel is. In the main sequence star, the fuel is hydrogen. At the next stage, it's helium, etc., etc. This process continues. Can I just say that when we talked about this before and we said the core collapses, the outside expands, we called that a red giant. Red giant. But now we don't call it a red giant now. For the large stars, we call it a supergiant. It's a small change in terms, that's all. New fusion reaction starts, blah, blah, blah. This process continues until the core becomes degenerate, at least as far as the electrons are concerned, and electron degeneracy pressure sets in, is created, occurs. Okay, and it's exactly the same, except for such large stars, the collapse of the core, and it's a larger core, of course, a larger core than the smaller stars. The collapse of the larger core has far more energy involved. Because it's larger, there's more mass there, the density of the bigger stars is denser. And as it collapses, there's a lot more loss of GPE, and the kinetic energy associated with the conversion of GPE to KE is much more energetic, and has far more energy involved. And as electron degeneracy pressure sets in, it cannot halt the collapse. Now, I just want to stop there for a second, because the question that comes into my head when I say that is, how can it not? How can it not halt the collapse? As the core continues to get smaller and smaller and smaller, there is no doubt that the energy levels get bigger and the energy spacings get bigger. You cannot, there's no denying that. Surely, eventually, it has to kick in. Okay, a lot more energy. The collapse is a lot more energetic. But when electron degeneracy pressure sets in, surely it has to be able to stop it, because eventually the thing will be so small that the energy spacings will be ginormous. It has to work. There is no denying it, and that's true. The point here is not that electron degeneracy pressure is incapable of stopping this collapse. That's not the point. The point is that when electron degeneracy pressure first sets in, there is so much energy available that actually electrons can still be excited, because there is so much more energy available. And so when it starts, when the electron system becomes degenerate, it can still collapse because there is so much energy. It doesn't instantly stop. It just slows down. So for such large stars, the collapse of the larger core has far more energy involved, and as electron degeneracy pressure sets in, it cannot halt the collapse. The collapse continues for a short period of time. So ordinarily, In a lower star, lower mass star, we say, okay, stop now. It carries on collapsing. And the ions, so in other words, all the other stuff, the ions become so dense that they collide, break into lots of protons. So in other words, the ions all collide with each other, predominantly at the center of the core. The ions break up and combine with the electrons, because don't forget the electrons, when we talked about the sphere of electrons, they are all the way, it is a full sphere, it's not a shell. We end up with a shell of negative around that pulls back to create the planetary nebula, but the electrons are everywhere within that sphere. And the ions become so dense, I don't mean the ions themselves, by the way, I mean the ion system. The ions become so dense that they collide, break into lots of protons and combine with the electrons to form neutrons. So basically the process is this: a proton plus an electron becomes a neutron. Proton charge number 1, -1, 0. Baryon number. A proton is a baryon, an electron is not a baryon, and a neutron is. And that kind of works. Would have been nice if I'd done it central, so let's just move it central. That's the process. Now, this process is a bit like taking an object. Imagine that you had a table on the ground, of course, with a football there. And what you did was, move the football to there. That would not happen under normal situations, under normal circumstances. In order to move an electron, in order to move a football up onto the table, in other words, to increase GPE, you would have to provide the energy to do that. When you increase GPE, that is against what the universe is trying to do. The universe is trying to reduce potential energy. This process is against what the universe wants to do. And when I say that, what I mean by that sentence is that the nuclear potential energy in going from here to here, that is an increase in nuclear potential energy. It would not normally happen. In fact, if you just have a neutron on its own, it'll decay into a proton and an electron. Neutrons are unstable. Protons are not. A proton, if you have a proton just sitting there, it'll sit there forever. Protons are not radioactive. Neutrons are. They are unstable. So this is an energy absorbing process, and the only reason it can happen is because there's so much energy available to make this happen. You are literally forcing these protons and electrons together to form the neutron, and it absorbs energy. So this process absorbs energy. The neutrons are in a very small space. And of course, we understand now, i.e. very small l in our formula. They are confined. And therefore degenerate. The neutrons formed can not collapse because of degeneracy pressure. So it's almost like the protons and electrons are collapsing really quickly because it's such a big core that's collapsing. And when the neutrons are formed, suddenly the neutrons are moving more slowly. And they don't have enough kinetic energy to continue to collapse. And degeneracy pressure sets in like instantly for them. There were some neutrons, there would have been some neutrons there, but suddenly you've got a huge pile of neutrons. It's almost like if you can remember when we drew the states, the 111 and the 112, 121, 211, all those states, some of them were occupied by the relatively small number of neutrons. There would have been a whole set of states available for just neutrons. Every single type of particle that is in the core has its own values for h squared over 8ml squared, m1, n2, n3, all that jazz. And there was a certain number of neutrons, whatever that number is. It would have been a large number, of course. But suddenly, huge numbers of protons disappear and huge number of neutrons suddenly appear as electrons combine with the protons to form neutrons. And it suddenly fills up all of the states. It suddenly occupies huge numbers of states. So the halt is incredibly abrupt. So the neutrons formed cannot collapse because of degeneracy pressure, and we call that neutron degeneracy pressure. The collapse is very, I don't know whether I like using this word, very abrupt. I don't know whether that word is like has general understanding, i.e. the delta t is very small. It happens in a very small period of time, and a huge shock wave is produced, which is called a supernova. A supernova is the most explosive event that we think is possible, as far as we're aware, in the universe.
So what about when two neutron stars collide? Isn't that pretty big as well?
Yeah, that's if two neutron stars collide, then depending on the size of them, no, it has to. If two neutron stars, and there's nothing weird about the neutron stars, if they are typical of sizes of neutron stars, I'll give you the mass numbers in a second, then that would have to form a black hole. But that's another supernova. It's a similar type of process, and they're both called supernova. So the outer material explodes into space. That's called a supernova remnant. And I would encourage you to have a look on the web. Type in Google supernova remnant and just click on the images, because the images look like a serious explosion has occurred. But if you look up planetary nebula, so look up those two things, that and that, The planetary nebula, it gives you the impression that it's a gas cloud nebula that forms planets, planetary. It isn't at all. It's nothing to do with planets. It's just that when we first saw them in the night sky, they have a relatively spherical or elliptical shape, and that's what we thought we were looking at. We thought we were looking at planets forming, but it's nothing to do with that. It is the outer part, in other words, everything but the core of a star that's less than 8 solar masses. And when it gets blown into space, when electron degeneracy pressure sets in, when it gets blown into space, it sort of maintains its shape somewhat, and it's a uniformly spread out, and it obviously, because it dissipates, it gets thinner and thinner, gets less and less dense as it expands. But when you see them, if you look at the pictures of planetary nebula, you'll see that they are generally quite pleasant to look at, in the sense of a nice sort of symmetric shape. I'm assuming that symmetry is something that we like, and I can show you. Let me just show you. Where's my mouse gone? Show you. If I just type here. Nebula. Click on images. These are typical images of planetary nebula. If you look at this one that let me just try do that one. Let's have a look at that one. Let's have a look at that one. That one's kind of interesting. That one. If I look at this one here, you can see the shape. It's not beautifully spherical, sort of elliptical, sort of rugby ball shaped, but you can see there's something at the center, and that's the white dwarf at the center. And this is getting blown out. This is false color, by the way. That's another one. There's the white dwarf at the center. Another one with a white dwarf. Sometimes I think this one. No, this one. It's not obvious. I'm not convinced that there is the white dwarf at the center. I don't know, but you can see that there are stars in the background here, and the light from the stars is getting through the gas cloud, because I can see them everywhere. And I'm not sure whether the white dwarf is luminous enough for us to clearly see it there or not, because remember, the white dwarf will be very small, and these things here in the background are full-on stars, I imagine. In fact, that one looks red where the mouse is, so I would assume that since it looks red, that star, for example, and maybe those two might be red giants, which are far more luminous. So I'm not sure whether that at the end of the finger there on the mouse is the white dwarf or not. It might be, but again, you get this sort of shape. Whereas if you look at a supernova remnant, oh, that's the second one down, and you look at what a supernova remnant looks like, then you have this kind of shape, and it looks far more sort of disastrous in the sense of an explosion. God, it's beautiful. Jeez, that's amazing. Not quite so beautifully smooth and well defined. Yeah, I don't think I want to say anymore. So supernova remnants, they look like they've had a lot more energy kicking the hell out of them. Okay, back to this, and let me get rid of that. So again, if you want to see some more, then have a look at those. Now, in the supernova, in the explosion that occurs, that is the supernova, there is a huge amount of energy. So this is a final point about supernova. And it's all about the importance of supernova. Or supernovae. We've got a white dwarf is largely carbon, nitrogen, and oxygen. In a supernova explosion, there is so much energy. There is so much energy that elements above iron in the periodic table that's not how you spell the word table are created. Now I remind you that just as a small aside here, if we were to plot nuclear potential energy against mass number, then it looks like this. And the universe is trying to reduce this. That's 56, and that's iron. So the universe wants to make iron, and if you allow the universe to do what it wants to do, there would be no elements above iron in the periodic table. The only reason that they're created, the only reason that all these are created, is because there is so much energy in that explosion that basically ions are thrust together to form these heavier nuclei. I can't remember what I said. White dwarf is largely common oxygen, full stop. In a supernova explosion, there is so much energy that elements above iron in the periodic table are created. This is, now I'm lying to you slightly. This is the only way we know of to create elements above iron. It's in a process. This just becomes now a little piece of memory in a process called the R process. R stands for rapid. It's a really quick process in this explosion. I'm lying to you slightly. We are way beyond A level and IB now. There is another there's basically two processes. I suppose I could have said it that way, couldn't I? There's two processes. One is called the R process and the other one is called the S process. R stands for rapid, S stands for slow. There is actually a slow way of making elements above iron in the periodic table, but this is the main one. So this is how the periodic table, with all of its parts, has come into existence, as it were. This is how the universe has created all of the elements above iron in the periodic table, and you are made of many of those. So lots and lots and lots of the atoms inside your body must have come, as far as we're aware, because we don't know of another way of doing it, they must have come from a supernova explosion in the past. And the S process is also part of a supernova explosion as well. I didn't want to suggest that the S process is something completely different. It's not. R process and S process both occur as a supernova happens. And that's why supernovae are incredibly important, because they're part of the way that the universe, they're the main way that the universe enriches itself with the sort of periodic table, of which our kind of life to some extent depends on. So yeah, okay. Now let's just talk about masses for a second, because I'd like to get to Sid's comment. Mass values. Okay, a white dwarf has got a maximum mass, whoops, of 1.4 solar masses. Now, obviously, the sun, when the sun creates, when the sun dies, that'll not be a great moment for humanity if we still exist. When the sun dies, it obviously won't produce a white dwarf of 1.4 solar masses, because it's only one solar mass itself. The size of the star, and the reason I'm saying it like this, guys, is because very often when you read textbooks, they will talk about mass values, because the mass is the big thing that people talk about. Physicists, astrophysicists talk about when they talk about astronomy. And they talk about mass values, and it is not always obvious whether they're talking about the mass of the star or the mass of the core. So here I'm talking about the mass of the core. The core becomes the white dwarf. The maximum value of a white dwarf is 1.4 solar masses. Now, since we think that stars up to about 8 solar masses become white dwarfs, and above that they become neutron stars, that means that a star of 8 solar masses will produce a 1.4 solar mass white dwarf. It's not a ratio, by the way. It's not like, okay, 1.4 out of 8, it's going to be something out of 1 for the sun. It doesn't quite work that way. But basically, white dwarfs can be different values up to a maximum of 1.4, which is called the Chandrasekhar limit. I'm not, I don't know how you spell that, so I'm not going to try. Okay, now neutron stars. Now, neutron stars, they have a mass limit as well. So a neutron star, the mass of a neutron star, NS, is greater than 1.4 solar masses, of course, because if it was there, it would be a white dwarf. But it's less than, okay, and this is more uncertain. The actual value it's less than. In other words, the biggest value that a neutron star can be is subject to some uncertainty. As a rough value, it's 2 solar masses. But I've read some pieces of literature where they'll talk about 2.1, others where they'll talk about 2.2 solar masses. So it's around 2. It's not a huge range, to be truthful. 1.4 to 2 or 1.4 to 2.2. Okay, so that's the maximum size for a neutron star. Let's just talk about the black hole. Very large stars. Now, a very large star is where the mass is greater than, well, actually, let me just let me put the range in. It's 30 to 40 solar masses. The mass is greater than that and less than approximately 100 solar masses. So it's above the mass limit for what a star that would become a neutron star, and less than about 100 solar masses. 100 solar masses is approximately is the maximum size that a star can be. Now, if you look in textbooks, if you look on the web for the size of different stars, you will see that there are lots and lots of examples of stars that are over 100 solar masses. And there's two main reasons for that. One, it may be that we're seeing a star, but it's actually not a single star. It might look like a single star, but we think it's two or three, because most stars do not form as a single star on their own. The majority of stars are like doublets or triplets. They're not single stars. And it may be that we're making a measurement of something and it's more than one star actually that we're looking at. That's the first issue. The second one is stars do move through space. It is not impossible for stars to collide with stars. So you could have two huge stars and basically they collapse into each other and make a bigger star. Or I suppose there's a third one which is linked to that second one. You can have two stars, which is quite common, in orbit around each other, and if one of them is much bigger than the other, it can end up sucking in material from the smaller star and making itself even bigger. So you can definitely, we have lots of evidence, empirical evidence on the fact that stars can interact with each other and exchange material. Now, in very large stars, the process as they die is identical to a neutron star, except the collapse is so energetic, neutron degeneracy pressure is not enough to halt the collapse. Now, okay, so I'm left then with the statement, well, surely neutron degeneracy pressure eventually, must be, just like we said, electron degeneracy pressure eventually would need to be. The problem is that the core collapses to such a small size that the gravitational field, because if you remember, and forgive me now guys because I can't, Sid, you've done because you're the odd one out here with respect to the educational systems because Paul's not here. You've done gravitational fields?
Yeah, I did that.
Yeah, and Kristin, have we done it? Or have you done it with Mrs. Edwards?
I think we did it with Miss Edwards. Okay,
but basically when we draw gravitational fields, if we take a mass, m, we draw the fields like this. The definition of gravitational field strength is force per unit mass. Because F over m is an acceleration, we also have F over m is equal to g. So gravitational field strength and acceleration due to gravity are the same thing. That doesn't work for electric fields, of course. The definition of electric field strength is force per unit charge. F over Q does not equal, there isn't an equation, F equals QA. So F over Q is an acceleration. That equation doesn't exist. So a gravitational field strength is the same as the acceleration due to gravity because of F equals ma. So the definition of gravitational field strength is force per unit mass, but we draw fields as collections of lines. If you wanted to know the direction, because if you look, F over M is a vector. That's a vector, that's a scalar. A vector divided by a scalar is a vector quantity. Field strengths are vector quantities. So they have a direction. And the direction of a gravitational field is the direction that a unit mass would move if you held it and released it from rest. So in other words, if I held an object in this room now and let go of it, it would fall. Because I'm not giving it a velocity or a speed, I'm just holding it and then releasing it. It will follow and be accelerated along the gravitational field lines. So that's why in this room, they would look like vertical straight lines. They're actually converging towards the center of the Earth, but over this kind of distance, they'd look like parallel straight lines, vertical straight lines. That's why we draw it like this. So they are straight lines heading towards the center of the mass. And the direction, of course, is inwards, because that's the direction a unit, I should say, if I'm being explicit, a unit point mass would move, like that. And when we draw fields as bunches of lines, we basically say that that would be quite a strong field. I haven't put the arrows on for a direction. That would be a strong field compared to that, because the strength of the field is indicated by how close we draw the lines. And this explains, of course, that if you look how close those lines are, they are closer than when you're there. And this tells us the field strength gets weaker, the number of lines per unit area decreases as you move away, because the lines are diverging. So this all kind of makes sense. So if you like, there are two definitions of field strength. One definition is force per unit mass. The other definition is number of field lines. We use the Greek symbol phi. It can be capital, which looks like that, or lowercase. It doesn't really matter. Per unit area. Those two definitions are equally correct. If they ever ask you, just this is for A level and IB, if they ever ask you to define gravitational field strength, this is what they're after. They are not after this. And I do not believe that they would give you the marks for this. I ended up in a kind of a YouTube discussion recently with somebody about the fact that in an A level or an IB exam, surely if they asked you a question and you gave the correct answer, but it wasn't the answer they wanted, you would still get the marks if you'd given the correct answer. And sometimes that's correct, and sometimes it's not correct. Sometimes I've kind of dropped into exam mode here, forgive me, but sometimes they will ask a question and there will be a clue in the question as to how they want you to solve it. And if you don't pick up on the clue and you solve the question in a different way, you run the risk of not getting all of the marks. However, there are some things that, and this is more tenuous, there are some questions they can ask where there isn't a clue. There isn't a clue in the question, but they just expect you to know what they want. And this is the case for definitions. They expect you to be aware that if we ask for gravitational field strength or electric field strength, this is the one we're after. We're after force per unit mass or force per unit charge. Interestingly, just to finish off this little bit of extension, there are three fields that you need to be aware of. And the three fields, of course, are gravitational fields, electric fields, and magnetic fields. And the definition for gravitational field is force per unit mass, because mass produces gravitational fields. The lines, they begin and end on a mass. And we can also write magnetic field lines, the number of lines per unit area. And we have a flash word. We call that flux. It just means field lines. Electric, force per unit charge, or we could have the electric flux per unit area, because charge creates electric fields. The problem is no quantity creates magnetic fields. The fundamental, really important difference between magnetic fields and gravitational electric fields is magnetic fields don't end. They are continuous. They don't have beginnings and ends. When you draw a magnetic field around a current flowing in a wire, it looks like this. It's circles. Or in a solenoid, and it looks like this. They carry on. Or if it's a bar magnet, it looks like this, but they actually carry on through. Magnetic field lines are not created by a quantity. So they're fundamentally different to gravitational and electric. They are more complex. So there is no force per unit where is the quantity that creates that field. Force per unit mass, force per unit charge. There isn't one for magnetic fields. So, but this still works. That definition still works for magnetism because we still draw magnetic field lines as like lines, and the closeness of them determines the field strength. So in magnetic fields, we still talk about the magnetic field strength as being that, but we don't have the force per unit something. That doesn't work for magnetic fields. Okay, anyway, the core collapses for the thing that is going to become a black hole. The core collapses to such a small size that the gravitational field, and this is why I went on about this this small aside here, as you get smaller and smaller and smaller, your field lines, when they leave the surface, get closer and closer and closer together. And so the core collapses to such a small size that the gravitational field becomes enormous. And so large that not even light, okay, I wrote the word light there, can escape. Now we call it, of course, a black hole. If you could see a black hole as like a black sphere, you are not looking at a physical something. You're looking at the region of space where if light goes into it or anything else, it cannot escape. There is something else inside. Everything that goes into a black hole is in there. The problem with black holes is that we do not know how to halt the collapse. i.e., we have no idea of how to oppose the gravitational force. So we don't know what's going on. Also, of course, we can't see what's going on. So we got no clues. So black holes are a problem. Black holes can be, there is no limit to the size of a black hole. Black holes can be any mass size. We believe that there are, I'm digressing now, we believe that there are black holes at the center of every galaxy. We don't know this, of course, because we haven't looked at every galaxy, but we believe that at the center of every galaxy is what's called a supermassive black hole. And that's just a flash phrase for saying, you know, ginormously massive, as in millions of times the mass of the sun. Our galaxy is called the Milky Way, and we believe there is a supergiant black hole at the center of the Milky Way. Now, it is an active question in astrophysics. Do galaxies form around supermassive black holes, or do galaxies form and then create a supermassive black hole? So which one? It's almost like a sort of a chicken and an egg type thing. Which one comes first? What's the sort of the order here? And we don't know. We don't know. But we do believe that there are, as I said, there are supermassive black holes at the center of every galaxy. That is our belief. That is not an empirical fact, because we have not looked at every galaxy, and nor will we ever be able to. So yeah, okay. So we're now in a. I'm going to kind of draw a line under this now, literally. We're now in a situation where we understand a little bit more about something called electron degeneracy pressure and neutron degeneracy pressure, and electron degeneracy pressure sets in and is strong enough to support against the force of gravity a white dwarf. When a neutron star forms, electron degeneracy pressure starts to set in, but there's so much energy that as the electron system becomes degenerate and starts to slow down, there is still enough energy to allow them to be excited, and that extra contraction that wouldn't happen in the white dwarf, that extra contraction is enough to allow protons to merge with electrons to form neutrons. In itself, that process is sort of complex, but anyway, and this is a process that then absorbs energy. So this slows down the collapse of the neutrons, and the neutrons that are created fill up the states at different energies, and the collapse is halted very abruptly then because of that. It's the subtle difference between the onset of electron degeneracy pressure in a white dwarf and the onset of neutron degeneracy pressure in a neutron star is the fact that for the electrons, you have the same amount of electrons compressing, getting smaller and smaller, not the electrons themselves, of course, the system, getting smaller and smaller, and degeneracy pressure sets in. For the neutron situation, you have a certain number of neutrons in the collapsing core, but when when protons and electrons merge together to form a neutron, suddenly you end up with a huge extra amount of neutrons. And that collapse then occurs incredibly quickly. And in part, there's more energy in the collapse, but also the abruptness, by comparison, the abruptness of neutron degeneracy pressure setting in, plus the extra energy involved, is why supernovae are so energetic. Yeah, I think that as I said, black holes, we just don't know. It's still an active problem, and if you're in any way concerned about why it is such an active problem and why we haven't come up with a solution, when we've obviously come up with some amazing ideas for everything else apart from black holes, it's in part the fact that heavy objects are normally, as in high mass, are normally very big. Those two things almost come together in nature all the time. High mass, heavy objects tend to be big, or the other way around. Big objects tend to be massive. They don't have to be, of course, because of density, but when we're talking about stars. And we have a theory that really nicely explains those. If classical physics can be used, we use classical physics. If we can't, then we use what's called Einstein's general theory of relativity. Okay, when things are very small, they tend to not be very massive. Electrons, protons, atoms, they're very small and they're not very massive. And we have a theory that beautifully explains very small but not massive things, and that's called quantum mechanics. The problem with a black hole is it's very small but also very massive, and this is unusual in nature, at least by our perception, and that means we need a gravitational theory that works with quantum mechanics, or as the physicists would say, a quantum theory of general relativity, a quantum theory of gravity. And we do not have an adequate one yet. We do have quantum theories of gravity, it's just that they don't work. So at the moment, this is a massive active area of research, and whoever solves this problem of how to come up with an effective quantum theory of gravity such that we can work out what the heck is going on in a black hole, etc., they will undoubtedly get the Nobel Prize without a shadow of a doubt. Because the other big moment in our time when this was important is, of course, the Big Bang. The Big Bang is where you have a huge amount of concentration of energy, but it's incredibly small. So if we understood black holes, we might be a little bit closer to understanding the moment of the birth of the universe. And that will radically change, I suspect, our understanding of the universe and of the properties of the universe. So it's a big deal.